Hello students, today we are going to see different representations of vectors. The first one we are going to see is the graphical representation. From schools you have been plotting a graph and you can draw a vector in that which starts from origin and the arrow heads towards some point. And this is x-axis, this is y-axis, this is your origin 0 0, and this is your graphical representation of a vector. So any vectors you draw, they are having arrow like structure which has some tail and head. Now this, let's say this is a point P, and which we can also denote as AB. This is also called as a point representation. So if you can see such a bracket which is separated by some numbers, this is in two dimension, so you can see only two numbers. But if they are three dimension or multi-dimensional, so in that case there will be n numbers in the bracket with separation of comma. So this can be also treated as a vector. Now the most common representation for the vector is a unit vector representation, and which is given by a I cap plus b j cap. So I am representing the same vector ab which was represented in point representation, and the same vector is represented in unit vector representation as a I cap plus b j cap. This means I am traveling a unit along I cap and b unit along j cap. So this is the same vector I am representing, but the representation is different. The meaning is the same. The last one is matrix representation. Here I can write the same vector in a column matrix. Okay, so this column matrix notation for a vector is also called as the vector in a vector space. So what is a vector space? You can say that there is a space in which we have some vectors. So that is basic definition of a vector space. Sometimes you can see a row matrix which also can be considered as a vector, but it is in a dual space. So all the row matrices also are a vector, but they are in the dual space. So I will shortly come to this point why we need dual space vectors and vector space vectors. But these are four basic representation. This is graphical representation which is shown by arrow. Then we have point representation which is numbers separated by comma in a bracket. Then we have unit vector representation which have unit vectors like I cap, j cap, k cap with their coefficients. So this we call as a linear combination of vectors. And then we have matrix representation. Then we see the inner product of a vector, or in general you have heard the term scalar product or dot product. So these three names are equivalent to each other. So what is the inner product? So if I have a vector, let's say a bar, and there is another vector called b bar, so I have to take a scalar product between these two vectors. Then suppose a vector is a1 I cap plus a2 j cap plus a3 k cap. Okay, similarly the vector b is b1 I cap plus b2 j cap plus b3 k cap, or in point representation I can write the b1 b2 b3 with separation of comma. So these two vectors are, if there are these two vectors, then the dot product of these two vectors is given by a1 b1 plus a2 b2 plus a3 b3. So the coefficients of I cap get multiplied plus coefficients of j cap get multiplied plus coefficients of k cap gets multiplied, and we get this final answer. This is a dot product or scalar product. So the answer is not a vector, it is just a number. Now there is one more thing we can consider. I have written this a1 I cap plus a2 j cap and plus a3 k cap. Sometimes we write this as, we can write this in matrix form like a1 a2 and A3. But you might ask, where is I cap, j cap and k cap here? So this is nothing but A1 into 100. So which this is nothing but I cap. So I don't need to write I cap separately in this matrix representation, and this is the beauty of this representation. Similarly, I can write A2 into 0 1 1, sorry 0 1 0. So this is another unit vector. So this is unit vector or basis vector, this is unit vector, and plus A3 into 0 0 1. So we can write in such terms, but we don't need to write always. So we don't need to write I cap, j cap, k cap separately. We mean this is a A1 I cap plus A2 j cap plus A3 k cap. So this is I cap representation in matrix notation, this is j cap, and this is k cap. Now when we have to do such dot product, you should remember in matrix notation, let's say these two are vectors. So this is 3 by 1 matrix, and this is also 3 by 1 matrix. So we cannot multiply this. So what we do, we convert this column matrix into a row matrix first only. Okay, I will shortly tell you what are these stars. So this is just, I have converted the matrix in vector space into matrix in dual space, and the second vector I will write as it is. And now we can easily multiply these two vectors. So we will get A1 star B1 plus A2 star B2 plus A3 star B3. So this is now you can see we can also write this as a linear combination of these vectors or the components of this. So AI star BI, there is summation between this, and the summation runs from I. So I can have values 1 2 3. So when I is equal to 1, this is equal to A1 star B1, then plus when I is equal to 2, A2 star plus B2, like this. So if we are dealing with the vectors in 3 dimension, we will have I is equal to 1 2 and 3. So I can run from this. And if we have suppose n dimensional vector, then we can have n number of the terms in this addition. Okay, so now you can check the dimensions of these vectors. So this vector has dimension of 1 by 3, and this vector has a dimension of 3 by 1. So you can easily see the dimensions here matches. Okay, and therefore we can take a product of this. Here you can see, here this is also 3 by 1. So okay, I will write again 3 by 1, and this is also 3 by 1. So this is 1 here, this is 3 here, they does not match, and therefore I cannot directly take the dot product or scalar product or inner product. Now why I have written a star here? This is because when we are dealing in a math for vector algebra, we most of the time take real numbers, but the matrices has use in quantum mechanics also, and there we treat this all vectors, they can contain some complex numbers. So if such case is there, then we just don't have to take the transpose of a vector or transpose of the matrix, but we also have to take complex conjugate of all the numbers. I will explain this with some example so that you can easily get. So let's take first vectors with real numbers. So I have these two vectors in 2 dimensions. So we can extend this in 3 dimension, but I just want to show how to do the things. So first of all, I have to convert this first vector in row matrix or in dual space. So I will just take the transpose of the matrix, and there are no complex number, so I don't worry much, and I will keep the second vector as it is. And now we can easily calculate the we know how to take product of 2 matrices. So first element of this here 1 into 1, okay, and then second in between there will be plus sign. So then 2 into minus 1, so 2 into minus 1. So you can easily calculate this. This is 1 and this is 2 into minus 1 means minus 2. So 1 minus 2 is minus 1, right? So the product of these two, the inner product of these two vectors is minus 1. So I will take one more example which will contain some complex number. So 1 and I, and another vector is 1 minus I. So I is a square root of minus 1, which is complex number. Now how to deal with this? So first thing is I have to take the transpose of first vector. So I will write 1i, but I is a complex number, so I have to take the complex conjugate, and therefore there is an extra minus sign. So when we have to take a complex conjugate, what we do? We replace I with minus I, or minus I with I. So here it is I, so I have replaced this with minus I. Now remember, we don't have to make any changes in the second vector. So I will write the second vector as it is. And now the usual process of our matrix calculation. So this 1 into 1 will be 1, and minus minus will get plus, and I into I is I square. But I square is nothing but minus 1. So 1 minus 1 will become 0. Therefore, you can see here we don't have any 0 here, but still we can get the answer equal to 0. So we will shortly see what property is this. But now you get idea how we can make a product or inner product of two vectors or two column matrices. Now let's see what are the basis vectors, or we also know them as a unit vectors, which we call which we call I cap, j cap and k cap and so on. Now when we have n dimensional vectors, instead of saying I cap, j cap, we number them like e1 cap, e2 cap, e3 cap up to en cap. So we can have different vectors, and we have to check their two properties. The basis vectors have two properties. First one is orthogonality, or orthogonal means perpendicular. In up to 3 dimensions we can call this as perpendicular, but after 3 dimension we cannot call it as perpendicular. Therefore we will use the word orthogonal. So as I told, we have some vectors e1, e2 and so on up to en. Okay, and I have to take the product. So let's say e1 and e2, we have taken product, and if this is a 0, okay, we should have cap over the vectors because they are vector. So if the dot product of this two vector is equal to 0, then we call the two vectors are orthogonal to each other. So here e1 and e2 are orthogonal vectors to each other. So this can have n number of vectors. So you should remember that if there are n dimensions, then we will have n different basis vectors orthogonal to each other. So in general, I can write this ei cap dot ej cap is equal to 0. But when this is I is not equal to 0, only then this is true. Okay. Then we will see another property which is called as normalization. So here we can have a dot product of the vector itself. So what is this? This is e1 cap dot e1 cap. So this is equal to 1. So this is called as a normalized vector. So e1 is normalized vector. So first of all, we will see what is normalization or what is norm. Okay, so norm is nothing but the magnitude of a vector. So this here you can see we write in the modulus. The vector is written in the modulus, and this is called as a vector dot product of this is a dot product of a vector with itself. So and we have taken this square root because you can see if I multiply a and a, this will become a square. So I have to take a square root. So this is called as a magnitude or norm, and from this word norm we have considered this as a normalization process or property. Now you can see I haven't taken here square root. This is because here is 1. So the square root of 1 or square of 1 is always 1. So we don't need to write here any square root. But if you have given a vector and you are being asked what is the what is the magnitude of a vector or a norm of a vector, then you have to take the dot product of that vector with itself, and then you have to take the square root. Okay, so this property can be generalized as ei cap dot ez cap is equal to 1 if I is equal to j, right? Now what we can do, we can combine these both properties and we can call the property as a orthonormalization. Okay, so we will see that. So for that we will define one symbol called Kronecker delta, which is written as delta ij, or it can be written as mn or delta pq, delta ab, whatever you can write. So this is equal to 0 1, 0 or 1. So this is equal to 0 when I is not equal to j, and sorry, this is equal to 0 when I is not equal to j, and this is equal to 1 when I is equal to j. So both the condition we can merge with just one symbol. Now as I am saying here, as I told, I and j can be replaced by any two symbols like ab, pqr, whatever you can write. So these are just dummy variables, they don't have any specific meaning, they are just indices. So they have values 1 2 3 4 and so on. The meaning you should remember for Kronecker delta is that if indices are same, then the answer is equal to 1, and if the indices are different, then the value is equal to 0. So now we can combine these two properties, orthogonalization and normalization, and we can write the property as ei cap dot ez cap is equal to Kronecker delta delta iz. Okay, so this is your orthonormality. So if any vector or any set of vectors are satisfying this orthonormality property, then such vectors are called as a basis vectors or unit vectors. So we will see some examples of unit vectors and whether we will check whether they satisfy the properties or not. So in general we have I cap and j cap. So we will confirm this in two dimension whether these two are satisfying the property or not. So first we will check the orthogonality. So for this I have to take the dot product or a scalar product of these two. So I have converted first vector into the dual space and second vector as it is. Now you can see 1 into 0 is 0 and 0 into 1 is also 0. So 0 plus 0 will be equal to 0. So final answer is 0. So both vectors are orthogonal to each other. Now you can also check the same in 3 dimension also. So this is I cap in 2 dimension. If I have to write I cap in, write I cap in 3 dimension, I should write this as 1 0 0. J cap will be 0 1 0 and k cap will be 0 0 1. Or if you don't have to say them I cap, j cap, k cap, you can call them as E1, E2 and E3. Okay, when the third vector is absent, when there are only 2 dimensions, these two part are not there, this is not there, so this is just same as this. So you can check for these 3 vectors. So you have 2 pairs of vectors. Here we have to check this, and in between these 2 vectors and also in these 2 vectors you have to check the orthogonality. Okay, so you have to take 3 inner products. Okay, now the second thing we have to do is we have to check the normalization. So whether the 2 vectors are normalized or not. So again I will take this first vector. So the norm we have to take of this vector. So I have taken this in the dual space into the vector in its original vector space. So this is equal to, you can see 1 into 1 is 1 and 0 into 0 is 0. So 1 plus 0 is 1. Similarly I can do for the second. So this is 0 1 and into 0 1. So again 0 into 0 is 0 plus 1 into 1 is 1. So this is also equal to 1. So both vectors are normalized and therefore these two can form a set of basis vectors. Therefore they are basis vectors. Similarly, in 3 dimension also you can do the same. You can see the 3 vectors are orthogonal to each other and they are also normalized, and therefore they can form a set of basis vectors. But sometimes what happens, I will give you one example why we need to change the basis. Suppose there is a system here with some slope. You have solved such kind of problems. So if there is a ball rolling over this surface having angle theta, so this is slightly bent. So what we do, we have mg acting over downward direction. In general we have this y and here it is x, or you can say this is minus y and this is x. So now here the motion is not in this direction, motion is along some other direction, and normal is here. So what we do, we change our axis system. Instead of this, we change this in we align them in the direction of motion and the perpendicular to this. So this is nothing but the change in axis. So I am not going to show you today how to change the basis, but I am going to show you one set of bases in 2 dimension, and we will check whether they are orthogonal to each other, and we will also check whether they are normalized or not. Okay, so we will see 2 vectors. So one of the vector is 1 by root 2 1 1. So 1 by root 2 is just a constant, so I have taken this common outside, and the another vector is 1 by root 2 1 minus 1. So we will check whether these 2 vectors are orthogonal to each other. So how to do? So I have to take the dot product or inner product. Now for orthogonality, the constants will not matter because they will not contribute to 0. So I am going to check whether these 2 matrices can give us 0 in their dot product. So the first one I have to take in dual space, that is 1 1, and the second one in original vector space, that is 1 minus 1. So now you can see, and the product of this 1 by root 2 and this 1 by root 2 will become 1 by 2. So I will keep this as it is here. Now this is equal to 1 by 2 as it is here, and now the dot product of these 2 matrices is 1 into 1 is 1 and 1 into minus 1 is minus 1. So 1 minus 1, and that is equal to 0. So 0 multiplied by something is 0. So therefore the dot product of these 2 vectors is 0. So they can be basis vectors, but we have to check the we have checked the orthogonality, but we have to check normalization also, because you can see if this 1 by root 2 is not there, instead of this there is some other constant, then also these 2 matrices will give me the answer 0. So the constant does not contribute in the normal orthogonalization, but they will contribute in the normalization process. So I will check this one, and you can check for this. Okay, so 1 by root 2, okay, I will show you in I will show you all steps. So 1 by root 2, I have taken this in the dual space, and then the vector, same vector again, 1 by root 2 into the original vector 1 1. So this is again equal to this 1 by root 2, and this 1 by root 2 will become 1 by 2, and then you can take the dot product of these vectors. 1 into 1 is 1, plus 1 into 1 is 1, 1 plus 1 is 2. So now this 2 and this 2 will get cancelled, and we will get the answer equal to 1. So this vector is normalized also. So this is the major role of this root 2, to make this vector normalized, and therefore this vector is normalized, and you can also check easily this vector is also normalized. So these are basis vectors. So instead of I cap and j cap, I can use this new vectors also. So these are basis vectors.